So, let us begin with a quick recap. Okay. So, so we have been looking at BCH and Reed-Solomon codes. So, primarily we saw construction and properties, right. So, that is what we saw. So, what is the construction? So, construction is through this parity check matrix. For the construction of length n, if you want block length to be n, you need you could take a primitive element from GF 2 to the m, and what is the property? N should be smaller than or equal to 2 power m minus 1. So, this is one choice. There are other choices, but we will just stick to this choice for simplicity. Okay. And then you construct the parity check matrix as 1 alpha alpha squared, so on till alpha power n minus 1, 1 alpha squared squared, so on till alpha squared power n minus 1, go all the way down to 1 alpha power d minus 1, alpha power d minus 1 squared, all the way to alpha power d minus 1 whole raised to the power n minus 1. This is a parity check matrix. All the binary vectors which satisfy H C transpose equals 0 will give you the BCH code. All the vectors over G of 2 to the m which satisfy the same equation will give you the Reed-Solomon code. Okay. So, that is the idea. So, for BCH, set of all binary vectors okay, and for Reed-Solomon we write it below this Cn okay. So, this is our definition and this is the construction, and what are the properties of the code. So, for RS it is very easy to come up with the parameters n, what is k? N minus d plus 1, and then minimum distance is exactly d, right. So, those were the parameters for the Reed-Solomon code. For the BCH code it is a little bit more difficult, right. I mean, to be very exact, but mostly you can come up with some numbers, but for instance if you take d to be 2t plus 1, okay, so that you have alpha power 1 all the way to alpha power 2t, okay. T is like the error correcting capability. Then you know this is going to be n comma what n minus, so should be careful here, you just say greater than or equal to n minus Tm, right. Can I say that? Think about it. Okay. So, see when I have d equals 2t plus 1, my zeros are, my roots are alpha, alpha square all the way to alpha power 2t. Okay. So, at most t of them will give me a minimal polynomial and the maximum degree for each of them is m. So, the maximum possible degree for the generator polynomial is Tm. Okay. So, I know the degree of the generator polynomial is less than or equal to Tm, which means k is greater than or equal to n minus Tm. Okay. So, in most cases this might be satisfied with equality, you might get an equality here, but in some cases it may be a strict inequality. For instance, the case when we had n equals 15 and d equals 7 or 9, I do not know, I forget what it is. It was one of those cases where there was an inequality, right. I think even d equals 5, this will not be satisfied. okay. So you would get something else there, if I remember correctly, go back and check that, but this is a rough inequality which will work in many cases, okay. So these are the changes in the dimensions, okay. First of all, BCH is a binary code, this is binary, and Reed-Solomon is 2 to the m array, okay. So hopefully this is clear, okay. So this is construction and properties, and I was pointing out how this is very non-trivial. If you start with just the space of all binary vectors, it is very difficult to come up with these codes, it is not so easy, these are huge spaces, in general you are able to do it, okay. So that is an interesting point here, okay. So this is construction and parameters, alright. So the next thing we have to address, of course, is decoding, right. So decoding is the most non-trivial task in this process, but before that I want to address encoding a little bit more in careful detail, okay. So I did do that briefly here and there, I think it's kind of clear to you what you should do for encoding, but I want to emphasize one thing, and in particular I want to emphasize systematic encoding, okay. What should you do for systematic encoding? We haven't seen that yet, so let's see that, okay. So let's first talk about systematic encoding. Okay. So if you want to do some encoding, there is one possible encoding which is very easy to do. If you are just interested in some way of encoding these things, what is the most obvious way of encoding this? Encoding BCH and Reed-Solomon codes. What I have been doing so far is to simply say, come up with the message polynomial m of x and then multiply with the generator polynomial g of x. So that has been like the simple way in which I have been describing things. So for some reason all these things are appearing here, which I do not know. Okay, let us see, hopefully it will not come up again. So it seems to think there is some mouse that is showing up, I have no idea why, maybe I am clicking this thing, this is in a very bad location. Okay, alright. So one way of doing the encoding is to simply say you have a message polynomial m of x, you multiply it with the generator polynomial g of x to get a code word c of x equals m of x into g of x. Okay, so this is very nice and it's eminently implementable, there is no problem there. Okay, the complexity is not very large, after all it's multiplication by a polynomial, it's not too difficult. Multiplication by polynomial, if you remember, is like convolution, right. So it's very easy to implement using some simple circuitry, it can be very easily done, there is no problem. Okay, but one problem with this encoding is it is not systematic. Okay, what do I mean by systematic encoding? What is systematic encoding? Okay, if it is systematic, okay, so this is in general non-systematic. Okay, so as in message does not appear as part of the code word. Okay. So hopefully that is clear to you. If you do m of x times g of x, there is no guarantee that the message will appear by itself anywhere, it is just a multiplication, it can go all over the place. Okay. So it will be good to have a systematic encoder. Why would you like a systematic encoder? Yeah, so at the decoder usually you decode to an estimate of the code word, okay, you correct the code word, and then from the code word, if you have a systematic encoding, you can simply read off the message bits. If you did not have a systematic encoder, then you have to worry about how to go back from the code word to the message, that is one problem. The other problem that also shows up often is the message usually will have a certain distribution which you can control, say let us say the uniform distribution or something, okay. So something that you can control. If you do an m times g, this does not seem like there is an obvious control over the distribution of the message or some property of the bits in the message that you might want to maintain. okay, at least for most of the bits there may not be, okay. So if you do an m times g. On the other hand, if you have a systematic encoder, the distribution of the code word also is controlled to a large extent, okay, some constraints are satisfied to a large extent, etc. So these things are useful. So systematic coding is useful for variety of purposes. So it's good to see if you have a systematic encoder, okay. So what I'm going to describe now is another way of encoding cyclic codes, okay. So in this other way of encoding, m of x will not map to m of x into g of x, but it will map to some other q of x into g of x, okay, but it will still be a one-to-one map, okay. So the way you come up with this is, okay, so you go from m of x to some other q of x, okay. So remember, this is what is m of x. So if you have an n comma k code, this is degree less than or equal to k minus 1 polynomial, okay. Q of x is also, let us say, a degree less than or equal to k minus 1, okay. So there are, so this will be a one-to-one mapping, okay. I will find a one-to-one mapping such that what, q of x times g of x, okay. This will be a code word from the code, right. This will be of the form sum r and then m, okay. So I am going back and forth between the polynomial notation and the vector notation, hopefully it is clear, okay. So I have written an ugly looking expression here, but hopefully it is clear to you, okay. Q of x into g of x is some c of x, which is a code word of the code, but it has the form r m, okay. So in particular, the last k bits of the code word of c of x equals m of x, okay. So that is the idea, alright. Is that okay? So basically, if you want in terms of polynomials, this will be r of x plus x to the power n minus k times m of x, okay, and the degree of r of x is less than or equal to n minus k minus 1. Is that okay? So I have to find a q of x which will give me, which will satisfy this equation, okay. So why did I do x bar n minus k times m of x? Because that is what will shift my m of x to that position, okay. So I push it to that position, right, and then add some r of x here. R of x should have degree definitely less than or equal to n minus k minus 1, okay. Only then it will not disturb anything in my message, it will appear as it is. So r will come here and do that, okay. Okay, stare at that equation for a while, okay, and tell me how I can find such a q of x and r of x. The notation I have used is a bit of a giveaway. I have to find a q of x and r of x. So I have to divide something by something, okay. I have to divide what by what? I want to find q of x and r of x. Q of x is going to be some quotient, r of x is going to be some remainder. So what should I divide by what? X bar n minus k times m of x, I have to divide by g of x, okay. So remember, g of x has degree equal to what? N minus k. So clearly when I divide, the remainder will have degree less than or equal to n minus k minus 1, and I satisfy every single thing I want, okay. So that is the formula for systematic encoding. What should I do? I should divide x to the power n minus k times m of x by g of x. What will I get if I do that? I will get a quotient q of x and a remainder r of x. The remainder r of x will have degree strictly less than or equal to, strictly less than n minus k or less than or equal to n minus k minus 1, and it will satisfy this equation, okay. So this is a valid code word, and it has the form that I want.
q of x times g of x equal to r of x plus
Hmm.
x power n minus km of x. We wrote it like that. Is it because we were in 2 power m? Because from this form it would have had otherwise
A minus sign. Okay. So you can adjust that minus anywhere you like. It's okay. Just find the remainder and attach a minus sign and push it to the side. So an arbitrary finite field. The question was the r of x is on this side. Now when I divided, I pushed the r of x to the other side. Okay. So when it comes to this side, it's going to be minus. Okay. But like I said, we are going to be only dealing with characteristic 2. So minus and plus are the same. There's no problem. But even if you have characteristic that is not 2, so you add a minus sign here and then you get the equation that you want. Okay, find the remainder, simply do a minus of that, you will get the answer. Okay, it's a very constructive method. Of course, it works only for, wow, it thinks my hand is the it's the stylus. So that's the problem with all these things. I think the more modern, what are these things called? They can differentiate between your hand and the stylus. Okay. So anyway, so that's systematic encoding. Hopefully it's clear. I haven't given you examples, but you get the general idea. Okay, but now it suddenly looks like you have to divide one polynomial by another polynomial, but this is division with remainder. Okay, so you can basically mimic your long division method. You remember your long division method, it's very easy to mimic that, and you can come up with a simple shift register circuit which will implement division. Okay, so you can mimic long division using a feedback shift register circuit. Okay, so it's a very common circuit. It can be done quite easily with D flip flops or what else, anything else also. Okay, so you can do that division also quite easily. So it's a easily doable operation. Do that and you get your answer. Okay. All right. So that solves encoding more or less completely. Okay, so you are now able to do encoding with an arbitrary error correcting capability. Right, any error correcting capability you want, you can go to a large enough block length n, choose a suitable Galois field and then find a suitable generator polynomial and then do this division and you get systematic encoding. Okay, so both BCH and Reed-Solomon you can do it, either one you can do depending on what you like. Okay, so the encoding part of the problem is solved. You have potentially you have a good solution. If only you can decode up to the promised error correcting capability. Okay, if you can correct t errors or d minus 1 by 2 errors, then you are good to go. Okay, so that's what we're going to see next, and that's in the decoding set. Okay, so I want to quickly remind you what we've been seeing so far in terms of decoding. The only thing we saw is the syndrome decoder, which is a good decoder, right? So it's not a bad decoder. So let me briefly touch upon that, and then we'll go back to then we'll see about Reed-Solomon and BCH codes. I think many of you might have forgotten what the syndrome decoder is. Yes or no? No? Okay, so it's good to remind yourself what it is. Okay, so let's do a simple example and remind ourselves what the syndrome decoder was. So if you have, let's say, a parity check matrix, which maybe looks like this. My favorite example parity check matrix. Okay, how do you do syndrome decoding? So the idea is, first of all, what is the picture? So you need a picture for the decoder. So you have a message M which gets encoded into a code word C, let us say k bits here, n bits here. The way we model it, we usually think of a binary symmetric channel with some error probability p, or equivalently you can think of something being XORed with the code word and that being the error vector. Okay, so E, which is n bits again, this is the error vector. so that you get a received vector R which is C plus E. What do you do to the received vector R? What is the first step? Compute the syndrome S which is H times R transpose. Okay, what I know in fact is okay. So, what I know in fact that this syndrome S which I compute as H times R transpose is also H times E transpose. Okay, so I know that is what I use in the reality, and then I have a distribution for my E, right. For my error vector E I have a certain distribution, right. It could be from the binary symmetric channel for instance, which means the all 0 core error vector is the most probable. Then what are the most probable error vectors? You want one weight error vectors, weight 2 error vectors, weight 3 error vectors, so on. Okay. So, then you make a table which we call as a syndrome table with error vectors and syndromes. Okay. So, you look up in the table and you get your E hat. Okay. So, you do a lookup. Okay. So, I want to write down the lookup also in the same box, so that I get E hat out. Okay. Then what do you do to the E hat? Add it to R, you get C hat. Okay. From here if you want you can read off M hat based on your systematic encoding or compute M hat. Okay. This computer seems to be thinking for itself too much. Okay. All right. So, how do you make this table? So, let me write down at least a few rows of the table. Okay, the table is quite easy. Okay, once again you do it in reverse. Okay, the 0 you can always very easily write, simply 0 0 0, and then for 1 0 0 0 0 0 you write 1 0 0 etc. Okay, so you make the table till you finish it off. Okay. So, basically the main thing I want to point out is the main equation you are solving is this guy, S equals H times E transpose. Okay. You have n minus k equations, okay, and you are solving for the vector E. Okay. So, if you have a distribution for E, you can do a maximum likelihood kind of solution, find out the most likely error vector. Okay. Another way of doing it is to say that my error vector has only so many ones. Okay. So, that is called the bounded distance assumption. Okay. So, you say I know my channel can introduce some errors, but it can introduce at most some t errors. Okay. It can never introduce more than t errors. Or another way of viewing it is saying at my decoder I will only correct up to t errors, beyond t errors I will just give up. I think I will say okay, this is way too bad, so let me retransmit or something. So, hopefully beyond t errors happens so rarely that it does not really matter. Okay. So, those are various ways of thinking about it, and in the syndrome decoder the way we thought about it was to say we will do maximum likelihood solution for this. Okay. So, we will find out which is the error vector which is most likely to have occurred, which will solve S equals H times E transpose, because otherwise how many solutions are there for this equation? 2 power k, right. There are n minus k solutions and n variables. So, there will be k free things that you can choose, and you can choose them in 2 power k different ways. So, you have 2 power k solutions, you have no way of picking any one if you do not know any information, right. So, you have 2 power k solutions, you pick any one solution based on the maximum likelihood method, or you can say I will do bounded distance, I know ahead of time that only t errors have happened. Okay. So, that also is possible, all right. So, let us you will get different answers based on based on something like this. So, for instance, So, for instance, let me complete that table. Okay, so for the previous thing, so I will complete the table and then we will use both these rules and see what happens. Okay, so I think this became a bit of a bad diagram. So let us say a long table. Okay, so if I make the syndrome table like we discussed before, let's go through and do this. Okay, so we will get a certain number of syndromes for these guys. So let me just write it down. You can go back and check whether I am making a mistake or not. I think you would get 110, 101, 011. Okay. Now, for the next syndrome, which is the only remaining syndrome 111, you have multiple answers, right. So, you have multiple answers even when you look at minimum weight, am I right? Even when you look at minimum weight, you have multiple answers. Okay. So, for instance, you can do first and last 1 0 0 0 0 1 or 0 1 0 0 1 0 or 0 0 1 1 0 0. Okay. So, if you use the maximum likelihood rule, okay, for the first 7 there are no problems, and for the last one you can pick any one without any problem. Okay. So, that is the maximum likelihood rule. On the other hand, if I want to say some kind of bounded distance rule, there is some confusion here, okay, right. You see there is a problem. So, suppose I say my decoder introduces less than or equal to 1 error. Okay. So, if I say my channel introduces less than or equal to 1 error, okay, then you only have these possibilities and you can do unique decoding. Okay. But if you say my decoder is introducing 2 errors, up to 2 errors, then you cannot do unique decoding. In fact, if you include the other possibilities for 2 errors, what are the other possibilities? There are 6 choose 2, 15 different 2 error patterns of length 6. Okay. If you include the other patterns, you will in fact keep getting the same syndromes. Okay. So, every syndrome now will correspond to multiple possibilities for each case. So, if I say 2 errors, what happens? If I say my syndrome is 1 0 0, what are the other possibilities for 2 errors? What else can give me 1 0 0 if I allow for 2 errors?
1 0 0 1 0
2 and 4.
2 and oh yeah, 2 and
2 and 4, 3 and 5, right. All these guys will give you 1 0 0, right. So, 0 1 0 1 0 0 or 0 0 1 0 1 0. Okay. So, for t less than or equal to 1 errors, you have unique decoding. For t less than or equal to 2 errors, okay, it is not possible. Okay, unique decoding is not possible. Okay, so how do I say that? I will say unique decoding is not possible. Okay. Okay, if you say ML, okay, if you say I want maximum likelihood decoding, then t equals 2 and all you should not consider. Okay, so t does not even enter the picture. I am only looking at the maximum probability which E would have occurred, and in fact when you have multiple choices with same probability, I can pick any one and that will be still ML. Okay, so that is the difference between ML decoding and bounded distance decoding. Okay, so if you say bounded distance decoding, you want in a way unique answers. Okay, so I want one answer which is within t of my received word. Okay, so those two problems are different. Okay, so you have, so hopefully you appreciate the subtle point here. Okay, so t equal to 2 we should not be correctable by bounded distance decoding. Okay, it will never work. Okay, but t equals 1 you can correct with bounded distance decoding in this code. Okay. So in general, if you do bounded distance decoding, okay, t equals d minus 1 by 2 errors are correctable. Okay, so that is where the error correcting capability comes in. If you do ML decoding, you might correct some 1 or 2 more other errors, but it is not, you can't be sure, right, you can never uniquely correct. Okay, so you know the probability of error will be okay, but then you can't say I am correcting exactly, you only can approximately say it. Okay, so ML is more about probability and bounded distance is a bit more algebraic, so you want exact solutions. Okay, so you can also view it a bit pictorially. So if you draw a picture and you put all your stars which are your code words, you remember this picture, we made this picture long back. Okay, so what are these dots? Okay, yeah, this entire space is, let us say, the binary vector space, and bit stars are your code words. If you receive, let us say, a particular guy here, okay, what do you do when you do bounded distance decoding? At beginning, starting at r with that received point as center, you draw a sphere of radius t. Okay, you draw a sphere of radius t starting with r. Okay, and if you find exactly one code word in that sphere, you declare that as your decoded code word. If you do not find anything, what do? You give up. Okay, that's how you do work with bounded distance decoding. If you do not find anything, you say I did not find anything, I failed. If you find more than one, then also you say you failed. Okay, there is some problem there. Okay, so sphere of radius, in sphere of radius t around the received word, look for code words. That is the idea in bounded distance decoding. If you find a unique code word, then you say I have decoded to that, else anything else happens, you declare a failure. Okay, there are two types of failure once again, you may not find anything or you might find more than one. Okay, both can happen with bounded distance decoding. Is that okay? Okay. So ML is a little bit different. What do you do in ML? Yeah, so what you do is from the received word, you look at every possible code word and then compute the distance from every possible code word and then pick that code word which was closest. Okay, so that is a little bit different. You do not restrict your space to within a sphere t around the received word. You look at every possible code word, find the distance from it and then pick the one which is closest. That is what you do in ML. Okay, so that is different from this. Okay. So it turns out for BCH and Reed-Solomon codes, there is a very efficient bounded distance decoder up to the error correcting capability, which is t equals d minus 1 by 2. Okay. ML decoding is hard. In fact, if I am not wrong, ML decoding is NP complete, so it is very hard, but bounded distance decoding can be done. Okay. In fact, you can do even slightly better than bounded distance decoding with very good complexity. There are some very advanced algorithms, we will not see all of that, we will only see a very basic bounded distance decoding algorithm which will work, which is very efficient. Okay, it is not exponentially complex in it, that is what I mean by efficient. Okay. Alright, so let us see that, and the particular decoder we will discuss, it is called the Peterson, it is due to 3 people, it is I think amalgamation of the work of all 3, Gorenstein Zierler decoder. Okay, so the first question in the final exam is leaked, the answer is right there, so you have to be pretty sure you know what P, G and Z is. Okay, I am only joking, okay, you do not have to mug up the names, it is just to give you the names. Okay, so the original ideas are from several people, but they also used these ideas. Of course, this decoder is hardly implemented in practice, and there are other decoders which are faster, etc. But this gives you a flavor of the kind of ideas that go into building a decoder for Reed-Solomon and BCH codes. Okay, so we'll do two things. First thing we'll see is a decoding of an example BCH code by example. Basically, we'll see decoding of a BCH code, of a 2 error correcting BCH code by example. I'll give you a simple example and we'll do the decoding. You'll see what it involves. Basically, it involves solving some equations. Okay, and then I'll present the general decoding method for PGZ decoding method for Reed-Solomon codes. Okay, so the BCH decoding method is obviously not the PGZ decoder. It's my own interpretation or somebody else's interpretation of that decoder. Okay, so let's see this example, and then I think you'll get a feel for the kind of ideas that go into decoding these things. Okay, so we'll go back to our favorite example. So the example is BCH decoding, and I will discuss the Reed-Solomon decoder in full detail. Okay, so but the example is also interesting as it gives you general ideas which are important. Okay, so first of all, how do we set it up? Suppose I say let us say in this example I will pick n equals 15, I will have alpha and g of 16 being primitive. Okay, so you have alpha power 15 equals 1, and then just the same as alpha plus alpha power 4. Okay, so you have this, and we'll look at the code with d equals 3, d equals 5. I am sorry, d equals 5 or t equals 2. Okay, 2 error correcting code. We saw this before. What are the 3 dimensions? 15, 3 parameters, 15, 11 and 5, right? Not 11, sorry, 15, 11 was 3, 15, 9 and 5, no, 7 and 5, 7, 5, right? You remember this code? What was the generator matrix for this code? I think 87641. Okay, so x power 8 plus x power 7 plus x power 6 plus x power 4 plus 1. Okay, 15, 7, 5 code. This is the generator polynomial. Okay, so what we'll do, so you remember in the syndrome decoder we were dealing with linear codes, and we were thinking of the message vector, code word vector, received vector, error vector, etc. Okay, so once you come to these BCH codes, we also view the vectors as polynomials. So we'll have a message polynomial which gives you a code word polynomial, and then you have an error polynomial which gives you a received polynomial, which will give you in fact eventually a syndrome polynomial. Okay, so we'll see all that. All of these things will become polynomials, and you can see why it is useful. Okay, and I'll also show you why it is simple and straightforward to think of it in terms of polynomials as opposed to vectors. Okay, and that's basically because of the structure of the parity check matrix. Okay, so let's do that. So for this specific example, you have a message polynomial which will be basically of the form m0 plus m1x plus so on till m6 x power 6. Okay, so k equals 7. So you will have this. If you want to really think of it as a vector, you think of it as a vector m0, m1 so on till m6. Okay, so basically 7 bits. Okay, so I won't do the same for all the other polynomials. Hopefully the relationship is clear to you. Okay, so you do the encoding. Let's say 15, 7, 5 BCH, maybe systematic encoding, okay, you would get a code word polynomial C of x. Okay. So, this is going through my channel, and the channel adds a error polynomial E of x, so that I get a received polynomial R of x. Okay. So, what is my parity check matrix? My parity check matrix is basically 1 alpha, alpha squared, so on till alpha power 14, 1 alpha squared, squared, so on till alpha squared raised to the power 14. Let me draw the whole thing. 1 alpha power 3, okay. This is my parity check matrix, and suppose my received vector is n minus 1, okay, and I have a received polynomial R of x. I have to now compute the syndrome. Okay. If I compute the syndrome vector S, I can write it as S1, S2, S3 and S4. Okay. So, if you do the multiplication with R transpose, you are basically going to get R0 plus R1 alpha. Remember, all these guys are bits. Okay. So, I am dealing with a binary BCH code, everything is a bit. Okay. R1 alpha plus R2 alpha squared plus so on till R14. Okay, I put n minus 1 there, so basically that is 14. Sorry, I thought I was doing it in general. Okay, so 14 R14 alpha to the power 14. Okay. So, now let us stare at it for a while. How do you write it in terms of R of x? It is basically R of alpha. Okay. So, that is why I said it is easy and nice to think of these things as polynomials as opposed to vectors, because of the structure of the parity check matrix. When I am actually doing H times R transpose and computing the syndrome, the first syndrome is simply an evaluation of the polynomial R of x at alpha. Okay. So, what would be the second one? S2 R of alpha squared. What will be the third one? Alpha power 3, and the fourth one would be R of alpha power 4. So, when you have this special structure for the parity check matrix, for which we define the BCH and Reed-Solomon code, using which we define the BCH and Reed-Solomon code, then evaluating the syndrome doing H times R transpose is the same as evaluating the polynomial R of x at the roots. Okay, what are the roots of my code? Alpha, alpha squared, alpha power 3, alpha power 4. I am simply evaluating it at the roots and I get my syndrome. Okay. So, there is more than one nice thing about in thinking about it this way. I will show you all the nice things about it. Okay. So, we have the first one, which is S1 equals R0 plus R1 alpha. I will write it down in the same format, plus so on till R14 alpha to the power 14. Okay. So, what happens when I square this? Suppose I square this and find S1 squared. What will I get? Okay, so it is going to be R0 squared. Remember, this is all characteristic 2. So, I can simply square the individual term and add it up. So, I will get R0 squared plus R1 squared alpha squared plus so on. But what is R0 squared? It is a binary number, right, 0 or 1. When you square it, you get the same thing. So, this becomes simply R0 plus R1 alpha squared plus R2 alpha squared whole squared plus so on till what? R14 alpha square raised to the power 14. Okay, the reason is Ri squared is equal to Ri. Okay, so each of these guys are binary. Okay, so this is the same. So in fact, what is this? R of alpha square, which is in fact S2. Okay, so in a way, when I restrict myself to binary codes, the second row of the parity check matrix is redundant. Do you see that? The second row of the parity check matrix is totally redundant. If the first row is satisfied, then the second row is also satisfied, right? Because the second row is simply the square of the first row. That is what I mean. Okay. If some vector is such that H times C transpose is 0, some vector C, then it is enough if I check the first row, second row will also be 0, square 0, you get 0. Exactly. So that's the nice thing about looking at it in terms of evaluation of roots. Okay. So this is quite interesting. The same thing you can do for S1 power 4. S1 power 4 will be R of alpha power 4, which is S4. Okay. So the only other non-trivial relationship that you have is S3, which is equal to R of alpha power 3. You can't do anything else with it. Okay. So S3 and S1 equals R of alpha are non-trivial syndromes. Okay, these are the real syndromes. The other syndromes are just dependent on these things, and you do not have to use them in solving anything. They will not tell you anything in your solution. Okay. So there is another way of thinking about it, which will also shed some more light, in case you are wondering where all this is coming from. R of x. Oh well, I am sorry. Before I go to R of x, okay, so it is not too difficult to see these things. So instead of thinking of the code word as satisfying this equation, you can equivalently think of it as C of x such that, instead of saying C such that this is true, C in binary such that this is true, you can say C of x in F2x such that what? C of alpha equals C of alpha squared equals C of alpha power 3 equals C of alpha power 4 equals 0, right? Am I right? So all these things are roots of C of x. That is my definition of the entire code. So clearly even here you see these two are redundant. Okay. Since C of x is a binary polynomial, if I have C of alpha being 0, then C of alpha square is also 0, C of alpha power 4 is also 0. Those are conjugates. It is going to bring with it all its conjugates as roots, because C of x is a binary polynomial. Okay. So in fact this definition you can change and say this is equivalent to C of x in F2x. Of course there is a degree constraint, I have not written it down. C of alpha equals C of alpha power 3 equals 0. Okay. So only the two syndromes are really meaningful. Okay, C of R of alpha and R of alpha power 3. The others really not anything new. Okay. So that's the information about syndrome. And then the next, okay, so if you want to look at that for a little bit longer, it's there. Okay. So the next observation that is important is moving from the received vector to the error vector. Okay, right? In the syndrome decoder, we had syndrome being equal to H times R transpose, but in fact we did not solve that equation. There is nothing to solve in that equation. We were able to write that as H times E transpose, and then we solved for the error vector E. Okay, either using the bounded distance method or the ML method or whatever. Find a unique solution in one of the two ways. Okay, so that's various ways of doing it. So let us see what happens here. Remember, R of x is C of x plus E of x. That is our model for the error in the polynomial world. Okay. Now what is S1? R of alpha, which is C of alpha plus E of alpha, but what do I know about C of alpha? That is 0. Okay, it is a valid code word, it is 0. So S1 simply becomes Okay, so I do not know what happened now, sorry. So, S1 simply becomes E of alpha, okay, because this guy goes to 0. So, similarly S3 also becomes what? E of alpha power 3. Okay. So, these are the two equations that we have to solve. Remember, the equation that we had to solve before was S equals H times E transpose. Now, we are solving these two equations, S1 equals E of alpha and S3 equals E of alpha power 3. Okay. So, now I am not going to go through the ML idea. So, let us see what to do if you have to do a bounded distance decoder. Okay. So, let us say I am going to restrict myself to a bounded distance decoder. Okay. So, if I am doing a bounded distance decoder, what is an assumption I can make about E of x? Remember, I am starting at R of x and I am only looking around R of x with the sphere of radius t. T in this case is what? It's 2. Okay, I am just looking at a 2 error correcting code. So, only 2. So, what is an assumption I can make about E of x now? It has only 2 terms. Okay, so E of x has only 2 terms. So, E of x will be of the form. So, if you do a bounded distance decoding, you can assume E of x has the form. Okay, E of x has the form let us say x power I1 plus x power I2. Okay, what are these I1 and I2? Yeah, 0 to 14. Okay. Is that okay? So, this is an assumption I can make about E of x. So, once I assume that E of x is like this, then I am looking only at a sphere of radius 2 around my received word, I am not looking beyond that. Okay. So, let us substitute back into this formula that we have. Remember, S1 and S3 I know already. Okay, S1 and S3 I know, right. These things are elements of what? S1 and S3 belong to what? Oh my goodness me. What are S1 and S3? It is R of alpha. Okay, alpha belongs to which field? GF16. So, S1 and S3 will be some alpha power something, right. So, it belongs to GF16, remember that. Okay, so, I have this equation now in GF16. Okay, it is not anything else. Okay, my goodness, think seriously, I mean, you have to invest in a new touch screen thing. I think this is, previously it was a little bit different because maybe it was, I do not know what is happening. Let us see. Oh, I think the taskbar went up. Okay, it's better, is it? It's one thing, but it's changing the page arbitrarily. So, anyway, so let us see, let me try and, how can I get rid of this bottom thing? There should be a way to do that. View page bar. Ah, see, there you go, it goes away. So, now that problem won't be there. Okay, so let us see. So, this is the problem you have. Okay, so if you plug in into this equation, I know S1, I want to find I1 and I2 such that alpha power I1 plus alpha power I2, and then S3 is what? Alpha power 3 I1 plus alpha power 3 I2. Okay, so these are the two equations that you have. Oops, and you have to solve for I1 and I2. okay, and these are equations in, remember, GF16, okay, so these are not equations in anything else, okay. So one thing that is a little bit weird about these equations is, equations are in GF16, but the solutions are integers, okay, so it is not a good idea to have such things, okay. So if your equations are somewhere, you also should have solutions in that same area that you are looking in, otherwise it will just get complicated. So what is one way of moving from integers to GF16? It is already there, but I want, instead of saying solve for I1 I2, I do not want to solve for I1 I2, okay. So what I will do is, I will do a very complicated change of variables, well it is actually a very simple change of variables. I am going to say x1 equals alpha power I1, then x2 equals alpha power I2, and you will see it will already begin to look a little bit better, okay. So what I will say is, instead of solving for I1 and I2, I will solve for x1 and x2, and now these guys are in the field I want, okay. So let us see, oh my god, it is now making, okay, I have given up totally, either I did something or, oh my god, okay. So now I think it is okay. These two guys are in GF16, okay. So this is not bad. Now I can write equations where everything is from the same field, okay, without any problem. So basically I have two equations, x1 plus x2 equals s1, and then x1 power 3 plus x2 power 3 equals s3, and these two guys once again are from GF16, and I have to solve for these two things, okay. So you have two variables, two equations. What is the standard way to proceed? You eliminate one, okay. So substitute, so find out x1 in terms of x2 and then substitute in the second equation. So let us do that. So let us say we find x2 in terms of x1. What is x2 in terms of x1? S1 plus x1. So you get x1 power 3 plus S1 plus x1 power 3 equals S3, okay. So if you simplify this, you see that x1 power 3 cancels, which is nice. Then what else will you have? So S1 x1 squared plus, well you have a 3 S1 x1 square, but 3 is same as 1 in my field, and then you have S1 square x1 plus S1 power 3 plus S3 equals 0. So what kind of an equation is this? Quadratic, everybody is suddenly afraid. So it is a quadratic equation in x1 with coefficients from GF16. Can you use your standard formula to solve it? There is a small problem with the standard formula. What? Yeah, there is a 2 that shows up in the denominator, which means at some point you have to divide by 0, which is not possible in GF16, okay. So your standard formula does not work, okay. In case your standard formula does not work, what will you do? Complete the squares? Yeah, you can't complete the squares. The standard formula comes from completing the squares, right. So if you cannot complete squares, what will you do? You have to do it in some other way, right. So it turns out you can do it, but one very simple way is what? I mean, there is one advantage you have with finite fields, that is that they are finite, yeah. So you try all the possibilities and then find the solution, okay. So that you can do in finite fields, which you cannot do in the real field or anything, but very eminently you can do that in the finite fields, there is no problem. In fact, even in the real fields you can do it, but anyway, it is a little bit more complicated. But in finite fields you can very easily build a circuit which will check one systematically one after the other and find out which the answer is. In fact, there is no general method beyond that. For quadratic you have a method, it is a bit more complicated, there is a method for solving quadratic equations, but beyond quadratic in finite fields you just basically test everything. I mean, how bad can it get, I mean you can, even if you go to a field of size 2048, you can build a parallel check for all the 2048 possibilities, and it will be done in like a few nanoseconds, I mean it is very fast. Okay, building these kind of circuits is trivial, it is no big deal. In fact, even pipeline it and run everything at the same clock and it will work very fast. Okay, so this is not a big problem. Okay, so it's a bit complex, but it's only as complex as the size of the field. It's not complex in any other way. Okay, so you solve this. Solve to find x1. Okay. Okay, so there are some curious cases that you have to consider. Okay, so before doing this, but for instance, S1 could be 0. Okay, if S1 is 0, what does it mean? Why should S3 be 0 if S1 is 0? S1 is just R of alpha. Why is R of alpha power 3? Why should it be 0 if R of alpha? Yeah, see, S1 can be 0 only when x1 and x2 are equal, which means there is no errors. So if you restrict yourself to 2 errors, you will not get the case when S1 is 0 and S3 is non-zero. Remember, you are restricting yourself to 2 errors, that is important. Okay. When you restrict yourself to 2 or lesser errors, you can never have the case that S1 is 0 and S3 is non-zero. Okay. But actually in practice, if you get that, it does not mean that something went something infeasible happened. It means more than 2 errors would have happened. Okay. More than 2 errors would have happened to make S1 0 and S3 non-zero. So at that point you give up. Your bounded distance decoder says I have not found anything within my radius. Okay, and then you give up. So solve to find x1. When I say that, I am also saying determine which situation has happened. Determine whether 2 errors or lesser have happened. Determine whether more has happened. We are getting it. So all these situations are captured in that. Okay, that's important. Okay, one easy way of solving is to brute force search, for instance, exhaustive search. Is one way of solving this equation. Okay. So what I want to highlight is these kind of equations are critical. Okay, so you can see why ultimately for an arbitrary BCH code with an arbitrary error correcting capability, you will ultimately get an equation of this kind. Okay, you will have an R of alpha which is the same as E of alpha, which will be x1 plus x2 plus so on. Then you will have an R of alpha power 3 which will be E of alpha power 3, which will be x1 power 3 plus x2 power 3 plus x3 power 3, whatever, if you have more than 2 errors. Okay. Then you will have a R of alpha power 5, okay, which will be x1 power 5 plus x2 power 5 plus x3 power 5, so on. Then you will possibly have a S7 which will be R of alpha power 7. You will write all these equations and you have to solve these kind of equations. Okay, so these are nonlinear equations in multiple variables, and in fact there exists a very smart technique to solve them using a set of identities called Newton's identities, which relate just power sums to some other polynomials. It can be solved. So it looks a bit scary. If you haven't seen it before, you will think it's cannot be solved, but it can be solved also. Okay, so there are methods that solve this. Okay. I'm sorry.
Yeah, you'll get two possibilities. One is x1, the other is x2.
Oh yeah. This will give you both the answers. Is that what you're saying? Yeah, you're right. Final answer. Okay, so the comment was, in this particular case, when I solve this equation, I'll also get the value of x2, 2 roots. Okay, so usually if there are no 2 distinct roots, okay, when you have an equation, quadratic equation with real numbers, you always expect 2 roots, right? Either with multiplicity, but it can be either one root with multiplicity 2 or 2 distinct roots. Okay, so that's how you expect it. In finite fields, all kinds of possibilities will occur. Okay, you might have no solutions, or you might have 2 distinct solutions, or you might have same solution occurring twice. Okay, only when you have 2 distinct solutions will there be 2 errors. If you have same solution occurring twice, then there would have been only 1 error. That can also happen. Okay, if there was only 1 error, what will happen to this situation? Yeah, S3 will be S1 power 3. So what happens? the constant term goes to 0. So, what are the two solutions? X1 equals 0 and X1 equals S1 itself, but X1 equals 0 makes no sense because X1 is alpha power I. Okay, so clearly it cannot be 0. So, being 0 is not possible. So from there you conclude that there was only one error and that was caused by that. Okay, so these are all various ways of figuring it out. So you have finally, so what is the moral of the story here? So you have a nonlinear equation in multiple variables which involves these power sums. You have to do some manipulation, change of variables, and get to one equation or one type of equation, and depending on how the solutions to that equation come about, you will have different kind of results for your decoder. If you have distinct results, distinct truths, then you will have good results. Or if you have any solution at all, you have good results, but if you have no solution or some crazy situation happens, then your decoder has failed. Okay, so that is the way to think about this. Okay. Okay, so I have some example, but I think if I do numerical examples, it's not so interesting when you see what is actually happening. There's nothing much beyond that I have to do. So what we are going to do next is to look at the Reed-Solomon decoder. Okay, so maybe we'll see a numerical example with the Reed-Solomon decoder. It's a little bit more interesting. So we'll see it at that point. Okay, so let me do at least the setup of the decoder for Reed-Solomon. It's a little bit more complicated. This is the PG, and what I'm going to do next is the PGZ decoder. I was about to say that. So now we go to the PGZ decoder. This is the way I describe it is for RS codes. Okay. So remember what is our setup again? We have a code word C of x to which an error vector E of x is error polynomial E of x is being added, and I get a received polynomial R of x. Okay. So if I have a Reed-Solomon code, this guy is now what? C0 plus C1x plus so on till Cn minus 1 x to the power n minus 1, and each of these Ci's now belong to Gf 2 power m. Okay. Now the same thing will hold for the other guys also. E of x will be E0 plus E1x plus so on till En minus 1 x to the power n minus 1, and each Ei will belong to Gf 2 power m. Okay, so same thing will happen to R of x also, R0 plus in fact Ri will be Ci plus Ei. Okay. So this is our general setup, and we want to find the syndrome corresponding to the received polynomial R of x. So if I have let us say a T error correcting code, okay, so how many syndromes do I have to find? Go back to my parity check matrix, 2T, right. So I will have my parity check matrix. What will be my parity check matrix? Remember, this is not binary anymore, so I can't simply throw away alpha squared. Okay, I have to do alpha square everything. Okay, I could throw away alpha square because it was binary. I can't do that anymore. So I have 1 alpha so on, 1 alpha squared, so on all the way to 1 alpha power 2T. Okay, so the syndrome will evaluate as S1 being R of alpha, which is E of alpha. Likewise, S2 being R of alpha squared, E of alpha squared, all the way down to S2T, which is R of alpha power 2T, which is E of alpha power 2T. Okay. So this is very similar to the setup we had for the BCH code, right. So not very different. Okay. So we will now have to make a bounded distance assumption on the error vector. Okay. So we will have to say I have a T error correcting code. So, I will only look at around my received word, I will only look at vectors that are at distance t or lesser away. Okay. So, what does that mean to E of x? E of x has less than or equal to t terms. So, we will have to take in general as t terms. Okay. So, how do I assume E of x now? So, remember previously I could simply say x power I1 plus x power I2, because binary there was only one non-zero thing 1. Now, I have some coefficient also. So, I have to put the coefficients also. So, we will take E of x to be of this form, E of x so we will say, let us say what should I say here, should be careful here. So, let us say W errors is what we will assume. Okay. So, I could set W equal to T, we will come to that, but let us start with W errors, it is good to do that. Okay. So, we will take it as y1 x power I1 plus y2 x power I2 so on till yw x power Iw. Okay. And what are these I1 to Iw? So, between 0 and n minus 1, and what about these yi's? Yeah, they belong to gf 2 power n. Okay. So, this is our E of x, and we have to solve for these equations. So, we will see how the equations become in the next lecture. Okay. So, we will stop here for now, there is about a minute left, maybe you can stare at this picture, see if it gives you some inspiration. Okay. So, stop here.